have 4 talks in this session. The first talk is on guarding orthogonal polygons with bounded Treewidth. It's a paper by Treewidth and Said Mehrabi, and Said will present the paper.
All right, thanks, Mikhail. Yes, my name is Said, and today I'm going to talk about guarding orthogonal polygons with bounded Treewidth. This is a joint work with my advisor at the University of Waterloo, Treewidth. So this is a variant of this well-known art gallery problem, where we are given a polygonal shape in the plane. And what we want to do is to basically guard or watch the entire polygon. So the guards are initially were modeled as points. So you can think of these red points each as a guard. And the point can see some point inside this polygon if the line segment connecting this guard and that point lies entirely inside this polygonal region. So for the one that I have on the upper left corner, the shaded area or the shaded region is its visibility polygon, or it can see these points. So in the original version, these guards could sit anywhere inside the polygon, but then there was also later other variants where the guards are called vertex guards. They can only sit on the vertices of the polygon, or boundary guards, where the guards can be located on the edges or the boundary of that polygonal shape. So as I said, this is a well-known problem. It's known to be NP-hard in both arbitrary and orthogonal polygons. Orthogonal meaning that the edges of the polygon are either horizontal or vertical. So they're restricted to axis parallel. It's also known to be APX hard, and we can't get any approximation algorithm better than a log n factor or something close to it. And in terms of parameterized complexity, very recently, last year, it was shown that it's also W2 hard, so we can't also hope for FPT, very likely. And there is a simple log n approximation algorithm for the problem as well. So because of all these mostly negative results for the original problem, there has been a lot of work on restricted versions of this problem, in particular orthogonal guarding, where not only my input polygon is orthogonal, I'm also going to define my guards to be orthogonal, or to see orthogonally in some way. So here I've listed 4 of them. On the top left, there is a staircase guarding where G as a guard can see a point if you can connect them using a staircase path, which is a monotone path going like as a staircase, right? Then on the other side, there is rectangular guarding where G can see a point if the rectangle defined by these 2 points, or more precisely, the rectangle whose diagonal is GP lies entirely inside the polygon. So if you can have such a polygon, then G will see P. K-Periscope guarding, it's similar to a staircase guarding, but here we only focus on the number of bends that you are allowed to have on your path. So G can see a point P if there is an orthogonal path with at most K bends between them. Here, the path doesn't necessarily need to be monotone, right? So it can be non-monotone. That's the difference, which makes the problem a bit more difficult. And finally, sliding cameras, where the guard is actually this time a segment, an orthogonal segment. And G can see a point if normal from that point to the segment lies entirely inside the polygon. So basically, if it's horizontal, it sees directly up and down. If it's vertical, it sees to its left and right. Okay. All right. So here are these 4 orthogonal guarding variants that we will look at. What we know about them, a staircase guarding and rectangular guarding are both solvable in polynomial time, but the running times are very slow. So n to 8 for a staircase, n to 17, which hides the log factors for rectangular guarding. And because of this high polynomial, there is a linear time tree approximation algorithm for rectangular guarding. K-Periscope guarding is NP-hard. Initially was shown for 3D, then in 2006 or 7 was shown that it's also NP-hard in 2D. And there is n-cube time algorithm, exact algorithm for simple grids, which are a very restricted kind of geometric object. They are not even in polygon. And the sliding cameras, as far as I know as of today, it's still open for simple polygons. With holes, it's NP-hard, but it's open for simple polygons. However, there is a constant approximation algorithm for it. So we can get a constant factor. All right, so I've worked on guarding problems a bit, and then I was wondering how we can extend our results here. If you look at the top box up there, we have polynomial time algorithms, but they are very slow. So one approach was to design approximation or faster approximation algorithms. But the other direction you can think of is how about to look at some restricted polygons and design efficient or fast exact algorithms. Okay? And that's how we looked at these problems and introduced bounded Treewidth polygons. And the definition, so I formulate the problem first as a kind of a discrete version. So we are given two sets of points, X and G, and we want to find a subset of G as guards to watch all X. So it's a kind of discrete, but it generalizes the original problem, right? So if you set G and X to the entire polygon, you get the original problem. So I will look at G and X from now on. And our main result was that we can solve all of these problems on bounded Treewidth polygons. So I've been saying this term for bounded Treewidth polygons, which is a parameter for graphs. So how we define it for polygons. So let me define it first before I use it further. So if you have a polygon, think of the one on the left hand side, you can extend from each reflex vertex until you hit the boundary of the polygon from other side, and you get a set of rectangles. You partition your polygon into a set of rectangles, and that's what we call as a pixelation of the polygon. And if you further divide each of these pixels into 4 equal size rectangles by drawing these red dashed lines on the right, you will get a one refinement, we called it, partition of the polygon. And if you take exactly this partition as your graph, so you have the vertices as these corners or intersections and the segments as your edges of the graph, this planar graph, we say that if this graph has a bounded Treewidth, then your polygon has a bounded Treewidth. So that's how we define a bounded Treewidth polygon. Okay? So it's kind of a new class of polygons. And we show that we can solve all these guarding problems on this type of polygons. Now, I first show you the approach, the outline, how we go to solve this problem, and then I'll show you a specific type of guardings and the way we did it. So you take the polygon, you have G and X here. Red points are G guards, blue points the points that need to be guarded. They can be an infinite set, not necessarily finite. The first step, we make them finite without affecting the optimal solution. And furthermore, we make sure we can actually make them in such a way that those G and X lie only on the corners of one refinement. So in the right hand side, you can see red points and blue points are all on the corner. Okay? And they are a finite set. So that's the first step. The reason we do that is because after that, we want to take or construct a graph based on those points. And they are related to the number of vertices in the graph, so we want them to be bounded, so we get a bounded graph. And for this graph, we show that if your polygon has bounded Treewidth, then this graph that I constructed below here has also bounded Treewidth. And our guarding problem becomes some graph problem in this bounded Treewidth problem. And what is interesting, or what is important about that problem is it can be expressed in monadic second order logic, or MSOL, which is something that we need, because if we can express a problem in this logic, then we can solve them in linear time using Courcelle theorem if the graph has bounded too. Okay? So that's basically the somehow big picture of how we want to tackle this. All right. Okay, so then let me show you. Okay, so before I show the algorithms, the way we make X and G finite, it's not that difficult. Basically, if you think of having, let's say here, an infinite or many points that needs to be guarded, and I have a guard outside of this pixel, let's say G here, that sees one of them, then based on the definition of the guarding types that I told you, it's not that difficult to see that. Then you can somehow either extend this path a bit further or cut it somewhere and extend it from somewhere else to see any other point also there. So I'm basically picking one point from each pixel as a representative. And if a guard sees that, it will see all of them. Okay? And you can do also the other way and make both G and X finite. So I won't go through details, but it's doable. You can do it for all these guards. All right, so if you believe that, then we have G and X two finite sets. We want to get a subset of G to guard or watch all of X. And they are the vertices of, or they're located at the vertices of the one refinement. Okay? Before I show you the staircase guarding, I first solve a sub-problem of it. Think of a guard which is a staircase, but it only sees the points that are above and to its right. So north-east guarding, right? So every guard sees only to its up and right. So if I want to solve that problem, I take my one refinement as a graph, and what I will do is I will direct my horizontal edges to the right and all my vertical edges up, so north and east. Okay? So then I will get this directed graph, and I know that my guards are some vertices of this graph, my points are some vertices in this graph, so I want to solve basically this reachability problem where I'm looking for a minimum number of guard vertices that from which I can reach to all of the points in the graph, right? And this is how you can show them in monadic second order logic or express them. And reachability of GPH means that there is a path, directed path, that you can reach to P from G in H. And so the graph has bounded Treewidth because the polygon has bounded Treewidth, and we just express it in MSOL. We can solve it in linear time. Okay. All right. So this was for northeast guarding. You can do the same for northwest, southeast, and southwest, right? All four main direction, because a staircase guarding can see exactly those four type of visibilities. Okay. And to solve the original problem of staircase guarding, we are going to combine those four sub-problems. So this is the graph for northeast. You do the same thing for northwest, southeast, and southwest. And for each of these instances, I have all these all these guards and points in there. And the next extra step is to introduce a vertex, a new vertex, for each guard and each point, and put them outside of these four gadgets and connect them to their corresponding vertex in the subgraph. So, for example, from G1, I introduce a new vertex v of G1, and I connect it from here, directed towards G1 in each of these instances. Okay? And then the problem becomes the same. Again, I want to find a subset of these VG1, VG2, and so on and so forth, such that from those I can reach to all these points that are again outside. And they are directed inwards, so I can get to them. Okay? And again, we can express it in MSOL. It's bounded Treewidth. We can solve it in linear time. All right, the next one is k-Periscope guarding. It's similar. It's not that different. And the way we do this one here is you take again your graph, but instead of having only the paths, I need to encode some kind of parameter to encode the weights. To encode the bends. Okay? Because here the path can go anywhere. We don't know which direction it's going, but the only thing we know is it has a bounded number of bends. So I take this graph, and at each intersection, I'm going to replace that vertex of the graph with a k4. Okay? And in this k4, if I'm passing through this vertex straight from left to right or up down, I have an edge with weight 0, because that path is not introducing any bend. Right? But if it happens that my path is turning at this vertex, I'm going in a different direction, then I need to take one of these diagonal edges, and that edge has weight 1, which means that you are turning, so you have one bend here, so you are making one weight increased by 1. Okay? So we do this for all the vertices. If you are at the boundary somewhere, then you don't need to worry about it. You just do it for the upper part. And two of them are connected with just an edge of weight 0, because it goes straight through. And at the end, for each point or guard, I introduce again a new vertex. So for P2, I'm introducing a new vertex VP2, and I connect it to all the vertices of its corresponding K4, and the weight of those edges are weight 0, so they don't have any weights. Okay? And the problem again is the same. You're solving some kind of reachability, but here it has a weighted reachability. And it's not MSOL, but it can be expressed in extended MSOL, which was introduced later, and for that one, we can still apply Corser's theorem and show that if we have a bounded Treewidth, we can decide it or optimize it in linear time. All right, I think that was it. So I don't have time for the two other ones, but I hope that these two at least gave you the idea of how we can apply similar ideas. For sliding cameras and the other one, it's a similar kind of ideas that you can use and show that the graph has bounded Treewidth, some kind of graph problem, and we can solve those as well. Thank you.
We have time for one quick question. Yes, go.
What do Treewidth bounded polygons look like? Or the converse, what does a polygon that is not a bounded Treewidth look like?
I can give you one example if it's okay.
Yeah.
So if you think of a staircase like this, if I extend these edges here, I basically get a big grid inside my polygon. So whenever I have a big enough grid that doesn't have a constant Treewidth, it can have a large Treewidth, so we can bound it.
Thank you.
Yes?
One more? Yes?
What are the trees in this case? What are the Treewidth? Yeah. So here, depends on how many steps do I have here, right? So it's order n or something. It's not constant. It's proportional to the number of vertices of the staircase that I have. I'm sorry?
How do you form it? Is it based on the directions that you form these?
She's asking where is the tree?
A treewidth is not a tree. I mean, it is a definition has a tree, but it's not defined. I mean, the grid, you can think of the grid as a graph. And then for that graph, you can look at its treewidth. You can construct its tree and see what is the treewidth.
So you are going by directions, that's correct.
Yes, we can direct it, but I don't see we need direction.
It does not mean that you split it into trees. It's more complicated than that.
Yeah, treewidth. So you take a graph. It's a parameter. You define its tree. You construct its tree decomposition, and then you measure its treewidth. So that's how it's defined. And it doesn't depend on direction or something, I guess.
Okay, we have to move on to the next talk. Thank you again.
Okay.